Welcome back to my office. Today we'll talk about errors and uncertainties in computation. If we look at slide 2, we'll tell you that errors are a part of life. You just can't go ahead doing computations without running into errors. And that doesn't mean you've done something wrong. It's not like walking across the street at a red light. It just means you're dealing with a finite computer and a finite amount of time, and there's some errors involved. It's very much like doing an experiment. There's uncertainties in experiment. Here on the computer, because the computer is finite, there's always uncertainties on the computer. We call them errors. You can think of them as uncertainties, would be just as good. Even though they're errors, you shouldn't be afraid to go ahead and do scientific calculations. People can say, they will say, they should say that you have errors in your computation. That's right, you do. But I will know how to control them. I'll know what size they are, just like any other type of good science. On the other hand, if your calculation ends up mainly with errors, mainly with uncertainties, then you're playing with what an official computer term would call garbage. Okay? It's no fun to play with garbage, so don't do it. If we look at equation 1 on slide 2, you'll see that we can model in a very gross, simple sense a general process on the computer by a number of steps or units, U. And we start at some place on the left here, then we move over to the right when we're N. Each step, here we call U1, U2, U sub N for N steps. Each step has a certain probability, small p, of being correct. And so you can ask the question, what's the probability after you have N, capital N steps, of all steps being correct, or the final end result being correct? Well, if the individual probability p for any one step being correct is small p, then the probability, the joint probability of all n steps being correct is just p raised to the power n. As an example, if we have 1,000 steps, which is not a lot for a calculation. After all, the computer moves along at millions, if not thousands of millions of steps per second, so 1,000 steps is not very much. So if we have 1,000 steps and the probability of each step being correct is 0.9993, so 7 parts in 10,000 can be wrong, then the probability of your answer being right is 1/2, which means the probability of your answer being wrong is 1/2, which means you do not have a good scientific calculation. Okay? So that's a problem. Where do these errors come from? So if you see slide 3, we list the 4 basic types of errors that you have to concern yourself with on a computer. The first one is an error that you concern yourself with in all of life. You're human, you make errors, you make blunders. Sometimes you're wrong. Sometimes you run the wrong program. Other times you run the wrong data. Sometimes you push the wrong key. These things happen. You have to learn to live with them. How do you learn to live with them? I don't know. You learn to be careful. You learn to try things again. You learn to be slow. You learn to take a break if you make lots of mistakes. Various ways. But just like everything else, you are concerned with it. There's another type of error known as a random error. You could say, I'm sitting here working away on my computer and a sunspot explodes on the sun, zap, cosmic ray comes through you, comes through your computer, it zaps electronics, and a wrong bit someplace gets recorded. Can that happen? Happens all the time. Can it affect the calculation? Well, it's very unlikely, it's very rare, but if you have a calculation that uses hundreds or thousands of millions of steps, then it's possible that one step is wrong because of power fluctuation, heat outage, anything. And the only way to know that you've gotten the right answer is to repeat the calculation. Now, if your calculation takes 20 seconds, it's unlikely you need to worry about this. But if your calculation takes 6 months or a year, then it's something worth considering. The main kind of error that we deal with, the kind that applied mathematicians study at length, is known as approximation error. And on equation 2 over here on slide 3, we have a very nice example. There we have the exponential series for e to the minus x. So it's a power series, and the full series that goes from 0 to infinity is in fact the exact definition of an exponential. So that's always correct mathematically. It's always the correct mathematical answer. But you just can't use that on the computer for a number of reasons. Mainly because you can't wait around to some infinite number of terms. It takes too long. You'd have to wait from now till infinity. That's a long time. And also because if you sum that many terms, noise would come in, as we'll see, and cause troubles. So the usual algorithm is given here by the middle term in equation 2, by that finite sum, where we only sum up to capital N terms. And that's the algorithm. And on the right side of equation 2, we say that algorithm gives us the right answer, e to the minus x, plus some error term. We never know exactly what the error term is. If we knew exactly what the error term is, well, then we'd get rid of it and we wouldn't have any error. Okay? But in a mathematical sense, there's always some error. In this case, it's just the remainder in the series. If the approximation is any good, if the algorithm's any good, then the remainder, the error, must decrease as you include more and more terms. Otherwise, you wouldn't call it an algorithm. You wouldn't do it. Ultimately, if you used an infinite number of terms, the algorithmic error should decrease to 0. Okay? The final type of error is round-off error. And we talk about that more on the next slide. And here we have slide 4, where we talk some more about round-off errors. Well, round-off errors exist because on a computer, everything is finite. We only use a finite number of bits to store most floating point numbers. And as a consequence of that, we have round-off errors. And round-off errors are very similar to the uncertainties you'd make in a laboratory measurement. The numbers are good, but they're not perfect. Okay? And the exception being any power of 2. A power of 2 you can represent exactly on the computer all the time. And as we'll talk about later when we talk about computer languages, you can extend the precision of numbers that you store to make them as precise as you want, give them infinite precision. But usually we only have finite precision. The problem with finite precision is that as you do a calculation with more and more steps, as we showed on the last slide, at some point the errors can accumulate and they can get bigger and bigger, and they can get as big as your result, or they could make your algorithm unstable. Sometimes your algorithm won't converge to an answer because round-off error comes in. And we end up with garbage. So here's an example we have on the computer. So on equation 3 here, you'll see on the left a very simple arithmetic operation which any, I don't know, 3rd or 4th grader should be able to do with no trouble. Okay, probably 6th grader. 2 times 1/3 minus 2/3. Okay? You know the answer should be 0, and you'd think, big fancy computer like these should be able to give us that as an answer. But if the computer only stores numbers to 6 decimal places, for the example here, you see that the number 1/3 would be stored as a series of 3s. So when you multiply it by 2, you get 6 6s. The number 2/3 would be stored as 0.6666, and then for the last digit would be rounded off, which is why this is called round-off error. So when we subtract 2 times 1/3 minus 2/3, rather than being left with 0, we're left with 0.0001 and 1. So while it's not a very big number, it's small, this is just in one step. If you do this step a million times, suddenly you have a number the size of 1. This error can get very big. There's no easy way around this other than being careful, other than understanding your algorithm. When we speak about numbers stored on a computer or written down any place, as we see in equation 4 here, we speak also about significant figures and scientific notation. So here we have this number A, which is a whole bunch, too many for me to tell you how many, whole bunch of digits and then a decimal point. Usually we write it in scientific notation, which means we have a number out in front between 1 and 10. Engineers sometimes use a number from 0 to 1. Scientists often use a number from 1 to 10. So this is scientific notation. So that's called the mantissa, and that mantissa is multiplied by some power of 10. In this case, 10 to the 19. 19 is called the exponent. Since the exponent is almost always a small number, you can assume it's stored exactly on the computer. But the mantissa, the thing out in front, all that long series of 1s, 2s, 3s, and so forth, is stored approximately in many cases. The first part in equation 4 here, the first part of the mantissa is the most significant part, and it's referred to as the most significant part. The second part is the least significant part, and it's referred to as the least significant part. On a computer, these different parts of a number are often stored in different words, so it matters. The least significant part is often not as significant, and it should not be as significant to you. It has errors which accumulate in it. So if we look at the next slide here, slide 5, we see a model for disaster. What's a model for disaster? Well, there's a rule of thumb, okay, for computers. If you subtract two large numbers and you end up with a small result, the result you end up with is suspect. It may well have very large errors in it. So to see this, we do a little bit of applied mathematics here. So in equation 5, we say on the left side, we want the computer to be smart. What's the difference, A, between a number B and C? Subtract those two numbers. Well, of course, the computer never stores B and C exactly. So the numbers stored on the computer we denote with a subscript C here in equation 5. So the actual computation going on is subtract the computer stored number for B and the computer stored number for C and see what comes out as an answer. Okay? Well, as you recall from the previous lecture, we said that there's such a thing as machine precision, and there's such a thing as precision of each number, and epsilon is roughly the percentage, it's roughly the machine precision. In this case, it's the error in each number due to machine precision. So the number B is stored on the computer can be written as the number B times 1, which is just B, plus B times some relative error, a small number, something like 10 to the minus 7th for single precision, 10 to the minus 15th for double precision. Okay, so it's good to the 7 to 14 places. Likewise, the number C is represented by itself, that's the 1, plus some error. So if we just do this multiplication as if this was what's really happening and divide by A, we'd see here that the relative precision of the answer, in other words, the computer's answer for A, which is A sub C, divided by the actual mathematical value for A, is equal to 1, which is a constant, always the correct answer, plus some errors which get weighted by the different values. Okay? So and this is true in general. Equation 8 here is true for when you have subtractive cancellation. If we imagine B and C being much the same size, and with errors, it's all right to make hand-waving arguments. We don't know what they are anyway, so it's just an approximation. So if B and C are about the same size, we have the answer is 1 minus B over A times the difference in errors. And the problem, as we started off saying, is if you start off with two large numbers, subtract them, end up with a small number, A is very small, B is large. So this is a multiplication factor. So even though the errors may cancel, sometimes exactly, but that's rare, somewhat, the amplification factor can get very large. And if you try to calculate a 0, you almost always have very large errors. So this is the worst possible case. And as you see in the example in equation 9, which is also something you'll be doing for your homework at least twice, when we look at this exponential series from minus x, we see that we know if minus x is, let's say, x is 100, e to the minus 100 is a very, very small number. And yet the series starts off with 1 minus 100 plus 10,000 divided by 2, some very large numbers, and it ends up with a very small number. That means all of these large numbers we start off with have to cancel off. And that means this is a very suspect algorithm. It's very error-prone. Okay? So let's get on to slide 6. And we can ask here, what happens when we have multiplicative errors? Is it any different? So if we look at slide 6, we can repeat the same kind of analysis. It's applied mathematical analysis. Here the number A in equation 10 is just the product of B times C. And whether this is multiplication or division, the errors will behave much the same. So assume this is also division errors. On the computer, the number a is represented by a sub c, and it's the product of the number represented by b times the product of the number representing c. And if we just do the multiplications again with the number plus some imprecision, and we drop epsilon squared terms, because if epsilon is small, epsilon squared is even smaller. And what we see is, oh, this just says the errors add. And that's true. If you have multiplication, division, you have the old rule that some of you have learned in your freshman physics or engineering classes, that when you take two measurements, you add the errors together. With two multiplications, two steps in a process, errors tend to add. You can argue, but you know, the computing gods are looking down kindly on me today. Why don't the errors subtract? Well, sometimes they do. You just can't count on it. And you don't want to build a bridge assuming that all the errors have canceled. You have to assume the worst and hope for the best. Okay? How do the errors add together? Well, you see here in the middle of slide 6 that sometimes the errors can subtract, sometimes they can add. So we have a model. And a model is one which we'll talk about more when we speak about random numbers and we talk about a random walk. But essentially, if you have, as you see in the picture here, if you have a step 1 in one direction, another step 2, 3, and if the directions are random, so if you add up a bunch of numbers or vectors randomly and you end up some distance, capital R, away from the origin, it turns out that the distance from the origin is proportional to the square root of n, where n is the number of steps you make. And we can apply the same model to a one-dimensional case such as this, where we're just adding positive and negative errors together, and say the worst possible case would be when we have capital N epsilon in the errors. The best possible case is when we have 0. The most likely case for a large number of steps is when the distance or the total error is something like the square root of n. And so that's the model we use. Okay? And that assumes that the errors are adding together randomly, which is a good assumption, particularly if there are many steps. There are some algorithms, such as factorials, such as other terms, where the errors may add coherently, and then you may end up with a factorial dependence on the number of steps. But those are exceptional cases. Okay, so and if we look at the bottom of slide 6, we see this interesting combination of numbers. One of the problems with scientific computers is that they're so fast. They do so many computations. And if you have them, you're going to use them. And you'll do bigger and better calculations. But let's say we do a calculation here which is 10 to the 10th flops. A flop is a floating point operation. That's not very much. As we've said, the clock speeds on these computers are in megahertz, so they can do millions, or gigahertz, they can do 1,000 million operations in a second. So running for 1,000 or hundreds of thousands of millions of computations is not unusual. So if we have a calculation that runs for 10 to the 10th flops operations, and we try to do it, say, in single precision, so that machine precision is about 10 to the minus 7, and we have 10 to the 7th times that as the error, we end up with a total error which is about 1, which means complete nonsense result. Okay? So obviously the thing to do is you use double precision, where the error, machine precision, is much smaller, and then you can run much longer. You can run a year, roughly, with this analysis. So let's see what the next slide shows. How do we do this? Well, one of the approaches that computational scientists use is to say we are, after all, scientists. We don't know all the math, but we have a computer that we use to compute the math, so why don't we use the computer to experiment with, tell us how good our computation is. One of the standard problems when I sit on a PhD or a master's degree thesis is to ask the student, what's the error like in your computation? Roughly, how much is it? And I may have no idea what he really did, or she did, but this is something every student should know, every scientist should know. So that's what we try to talk about here. If you have an algorithm you're using, there's some very basic questions. The first one is, does it converge? In other words, in a mathematical sense, does it give you an answer and then stop getting any better or any worse? It gives you a good answer. When you apply it on the computer, if you're summing a bunch of terms like we did with the exponential, the answer should converge to some number and then just change a little bit in longer, smaller and smaller decimal places. Okay? If it doesn't converge, then you don't have an algorithm that's worth using. You may as well quit. Okay? If it does converge, one likes to think, and usually it's true, that it's converged to the right answer, but that's not always the case. So if it's converged, another question to ask is how precise is it? And if it's not converged and it's given the wrong answer, that happens as well. Why is that happening? And finally, if you have an algorithm, how expensive is it? And expensive is another colloquial term on a computer, meaning how time-consuming is it? If it takes 1 second or 2 seconds, doesn't matter. But if you're running for a week or you're running for an hour, then makes a big difference. And the best way to speed up any calculation is to use a better algorithm, not to find a faster computer. Okay. So here on slide 8, we outline an experimental approach to understanding the error in your computation. Not every computation will follow this exactly, but if you have a feel of how you go about it, if you feel comfortable enough with the computer to experiment, figure out how the error is behaving, then you have a handle on your error and you're in control rather than these random walk demons behind you. So we'll talk about, above equation 12 here, we'll talk about the approximation error. The approximation error is another word for the algorithmic error. The approximation error, if we know what the exact answer is, would just be the difference between the exact answer and the answer obtained with the algorithm. Okay? So if we don't know the exact answer to your problem, and be honest, if you knew the exact answer to your problem, you probably wouldn't be computing it. So either you assume you know the answer, or you try to solve a problem very similar to the one you're really interested in, but you solve one for which you know the exact answer, and then you develop your technique, you perfect it on that, and then you move ahead to a problem where you don't know the answer. Okay? But we'll assume here you know the exact answer. The basic rule of thumb is the algorithmic error has to decrease when you use more terms. And usually it decreases as some power of capital N. So we see here on equation 12, we're assuming that the approximation error looks like some constant alpha divided by capital N to the power beta. Alpha and beta are unknown, but you can determine those experimentally. And this is not true maybe for small n values, but as n gets larger, when it starts converging, it must be true. We also know that another type of error, just sort of the noise in the calculation, the round-off error, is proportional to the square root of n times machine precision. So the big difference between equation 12 and equation 13 to note is that the algorithmic error gets smaller as you use more terms. The round-off error gets bigger. And at some point, if you let n get big enough, round-off error must get larger because it keeps growing and algorithmic error decreases. And that means that if you run long enough, you'll always have round-off error in your calculation. It'll always be approximation. It could be a bad approximation. Ideally, what you want to do is to have the minimum error in the total calculation. So as we see in equation 14, the total error is the sum of approximation error and round-off error, and we want that to be minimized. And the better algorithm you have doesn't mean that you've been smarter. It means that it converges more quickly, and if you use a smaller number of terms, then n is smaller and the round-off error is smaller. That's how we make it smaller. So let's see an example of this. So here on slide 9, in the figure, we actually have the results of 3 computations, which you yourself will be doing in a little while. So these are integration calculations, and this is the relative error in the answer as a function of the number of steps used. And you can use a calculation of this sort to actually determine what the values of alpha and beta are. So what you see here is that at first the error in the computation decreases like a straight line. Well, this is a straight line on a log-log plot, and that means the error falls off like the power of n. So this slope, which you can determine just by, rise over run, just by taking the tangent, is equal to the power beta. So you have a way of determining the power beta. And what's interesting is you see, the algorithm always does converge. It starts getting better and better. But then at some point it runs into this sort of rocky shelf. Well, that rocky shelf is noise. It's the round-off error accumulating. And our model says it roughly increases like the square root of n. Square root of n is a slow increase, and that's what we see here. Very slow rise in the noise at the bottom, with it jumping around. Jumping around means it's noise. We don't know exactly how it behaves, but it accumulates randomly, but it gets bigger. And the best you can do is when the total error is the smallest, is when the round-off error is about equal to the algorithmic error. Because after that, round-off error dominates. How do you do this on the computer? Well, we indicated one way. If you can plot this graph up, you can determine what alpha and beta are, and then you can to say what your error is at any one step in the calculation. Another approach is, well, what if I don't have a good analytic answer to compare with? Well, then what you can do is to say, I'll just look at my answer. Just look at the answer coming out of the computer and plot your answer up as a function of the number of steps used. And you should get crummy results at first, but then as it falls down, you see, the results seem to converge. They're getting better and better. And then if you push it further, you'll see, some noise comes in. So what you do is you say, it's converged at one point. Let's say it looks pretty good here. We've used n terms. So that's here on slide 9, right in the middle. If we use capital N terms, and it looks pretty good, if we use twice as many, but still it hasn't started to be noisy, that's a better answer. So you can take the difference between 2n and n as the same as the difference between the exact answer and the approximation, and use that for your error analysis. Finally, on the bottom of slide 9, notice that we've made these plots on a log-log scale, and it's logarithm to the base 10. If you don't have that on the computer, you can calculate it from the usual computing base log e. We can just tell your graphing program to plot it up. When we do that, this is the relative error. The number that is plotted here, or the power of 10, however you plot it up, gives you the number of digits of precision. So if the relative error here is 10 to the minus 7th, that means we have 7 good decimal places. So this is clearly a single precision calculation, because we're only getting, the best we can do is 7 decimal places. Okay? So, I think that's enough for this theory. As I said, the fun part of computing is doing it yourself. And you really now need to go outside, sit down at your computer, and try some of these things out. Make the computer have errors. See if you can break the algorithm. Remember, you don't do any harm by trying out these things and having the computer fail, but you learn a lot. So we'll get back after you've done this some more and learn some more. But now go ahead and enjoy stuff.